Hello students, this is Vivek from Shiv Jyoti Education Group. So today we'll start with the first unit of class 12th physics, which is electrostatics, and in this the first chapter deals with electric charges and fields. Okay, so let's start with charge. Now what is charge? Charge, as you all are aware about it, like you have read about it in physics, in chemistry. Like when we talk about charge, the first thing which comes up to your mind is positive charge and negative charge. Those are the two types of charges. Okay, so you should know what is charge. Charge is basically an intrinsic property, or we should say that it is a physical entity which decides the electric, magnetic, and electromagnetic properties of all the substances. So, electric and magnetic, you have learned about it in 10th class. But electromagnetic is something which is both the phenomena, electric and magnetic, going together. So, these all phenomena are, these come into picture due to this thing charge. Okay. So, positive and negative, we were talking about the types of charges, positive and negative. So you know that charge, when do we call an element to get charged or to lose charge? So it all happens due to electrons, as you have gone through a lot in chemistry, I think. So when a body loses electrons, then it gets positively charged, and when a body gains electrons, it gets negatively charged. Okay, so we can understand one thing, that whenever charge comes into picture, then an electron also comes into picture. Why? Because the charge on an electron is basically the smallest unit of charge which we can measure. Okay, you can see over here we have the units have been marked over here. It is shown over here, 1.6 into 10 to the power minus 19 coulombs. This is basically the charge on an electron. Okay, 1.6 into 10 to the power minus 19 coulomb, but as it is on an electron, so it would be negative. Therefore it is written over here that this is the charge on a proton with a plus sign, but here the charge on an electron, it is minus 1.6 into 10 to the power minus 19 coulombs. And this coulomb, what is coulomb? It is the unit to measure electric charge. Okay, so the first property which we came to know is the types of charge. There are two types of charges. One is positive and the other one is negative. Okay, so let's go further. The next thing which is shown over here is like when we talk about charge, like when elements can share electrons, then either they can share 2 electrons, 3 electrons, or 10 electrons. So they cannot share 2.5 electrons or 1.5 electrons. Why? Because like when we talk about an electron, then an electron is an element, basically it is an entity, it is a particle basically. So it cannot be like half electron or 2.5 electron, it has to be an integral thing. So that is another property which is an important property of the charge, which you should know. It is mentioned over here. It is called quantization of charge. As you can see over here, quantization of charge. What do you mean by that? That the total charge on a body can be written as an integral multiple of the least quantity of charge, that is 1.6 into 10 to the power minus 19 coulombs, which is charge on an electron. Okay, it is also shown as E. We also call it E. So generally we write like this: Q equals to NE. This is like the quantization of charge, but by in symbolized form you can write it as Q equals to NE. It simply means that the total charge on any body should be an integral multiple of the smallest charge, that is the charge of an electron, the smallest charge which we can measure. Okay. The next property which comes up is that charge is additive in nature. Additive in nature means like if you have 2 coulombs of charge and 4 coulombs of charge, then it makes a total of 6 coulombs of charge. Okay. Then the next property is that there are two types of charges, positive and negative, which we have already discussed. So positive and positive together would be called as like charges, and negative will be called as like charges, but positive and negative would be called as unlike charges. So this is a property that like charges repel while the unlike charges attract each other. Okay. So The next topic is Coulomb's law of electrostatics. This Coulomb's law basically deals with the attraction or repulsion between two charged bodies or two charges kept at certain distance apart. Let's say r distance. Okay. So this Coulomb's law states that when two charges, like if you have two charges q1 and q2 placed r distance apart, as it is shown in the picture over here. So if you have these two charges placed r distance apart, so the force of attraction or repulsion, whatever we say, that in between would be directly proportional to the product of the charges, that is, as it is shown over here, and it would be inversely proportional to the square of the distance between them. You can see over here. Okay, so when we solve this, the proportionality thing, like the force would be proportional to q1 q2 upon r square. We can write it like that. So that proportionality sign would be removed by a proportionality constant. So here is your proportionality constant, which is 1 by 4 pi epsilon naught. This is epsilon basically, this symbol. This is epsilon. We'll discuss about it. This is called electrostatic permittivity. This is permittivity. And when we would be talking about space, like vacuum or space, then we will write it as like this, epsilon naught. This is basically epsilon naught. This is epsilon, general epsilon. This is epsilon naught. This is permittivity of free space. Okay. So this is the formula for Coulomb's law, which says that F equals to k q1 q2 by r square, where epsilon is the permittivity. Now, permittivity, as it is mentioned epsilon over here, so it means that it depends on the medium. Like I told you that it would be epsilon naught. So when would it be epsilon naught? When we are talking about free space or vacuum. Okay, and apart from that it would be epsilon. And what is the relation between epsilon and epsilon naught? Here it is mentioned as relative permittivity, epsilon r. So epsilon r equals to epsilon upon epsilon naught. Okay. In general, we would be most of the time we would be talking about vacuum or free space. So you just need to remember this value over here, 1 by 4 pi epsilon naught. That is the value of k, which is mentioned over here. This 9 into 10 to the power 9 Newton meter square per Coulomb square. Okay, this is the value of permittivity of free space, which we would be using mostly in the numericals. And the value of epsilon naught, when we talk about it, is mentioned over here, 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square. Try to remember these units also, like you can derive them from the formula itself. Okay. So this is permittivity of free space. Okay, so let's go further. Relative permittivity, you know it now. Next is superposition principle. So superposition principle is a very easy concept. So what it says is, like, if you have three charges in the medium, q1, q2, q3 together, and if you have to like find out the charge, the resultant effect of these three charges on any single point, like let's say if you have to find out at this point. Okay, so what this would say is that the net force acting on any point charge is the vector sum of all the forces acting on the point charge in a system of point charges. Means the resultant force acting on this plus q would be what? Due to these three charges would be the resultant of these three forces, F1, F2 and F3. And resultant means the vector sum of F1, F2 and F3. Okay, this is superposition principle, that the resultant force on any single charge due to any other charges present in the system would be the vector sum of the forces acting on that single charge due to all the other charges. Okay, so it would be vector sum. You just need to remember that it is vector sum. That's the most important thing. Okay. Okay, so that's superposition principle. Now the next thing which comes into picture is electric field. Like as we discussed Coulomb's law. So now you know that if there are two systems, or if there are two charges or a more number of charges present in a system, then they would surely exert some force on each other. So why is that force over there? Like up till what distance would be the force? So you can understand it in terms of a magnet. Like if you place a magnet somewhere and if you are placing some iron objects, then the force on those iron objects would decrease if you will increase the distance of those particles, the iron particles or the iron objects, the more you will increase the distance, the force would decrease. So it means that some effect is decreasing. In the same manner, there is a particular area surrounded by this charge in which these charges exert force. Okay, that area in which any particular charge would be exerting force on any other charge is called electric field of that particular charge. You can see here the definition is also mentioned that it is a region or space around a point charge or system of point charges or a charged body within which at any point if a second charge is brought. Understand, like if it is a region or space around a point charge in which if any other charge is brought, any second charge is brought, then it experiences an electrostatic force. It experiences an electrostatic force. So that particular area is called electric field. Like you can see over here, if this is a plus q charge and if there is a del q charge, then as it is positive charge, so it would exert a force on this del q in this outward direction as it is shown over here. Okay, so that's electric field, the area in which any charge exerts a force. Okay, so when we'll talk according to Coulomb's law, if we talk about the force which this charge would be exerting, would be, this is k, I'll show it to you, this is k and this is charge 1 q1, another charge is this del q, divided by the distance between them, this distance r square. Okay, so this is the force which the charge capital Q would be exerting on the charge del q. Okay, now let's see. So the electric field over here, they say that the electric field intensity, if we have to calculate the electric field intensity due to any particular charge, then it is calculated as F by del q. Like as you have seen that del q was the charge over there in on which we were calculating the electric field intensity due to the charge capital Q. So this is the formula which you need to remember, that E equals to F by del q. You can even remember it like this, E equals to F by Q, where Q would be the charge on which we have to measure the electric field due to any other charge capital Q. Okay, you just need to remember this, that this is the formula for calculating electric field due to any charge small q. Okay, now we'll see what comes out to be the electric field intensity. Before we go that, you can just go through this. It is showing over here that F will be equals to Q into E according to this formula. If you multiply this del Q with E, then we get the formula F equals to QE. Okay, but this would be F equals to QE when Q would be positive charge, and this would be equal to F equals to minus QE when it would be negative charge. And this negative sign indicates that the force due to a negative charge would be in opposite direction as compared to the electric field. Okay, so here we got the force over here, we calculated previously, F equals to K, here we calculated it over here, yes, F equals to K Q1 Q2 by R square. The same force we are taking it over here, and according to our formula, when we use the formula E equals to F by del Q, then we'll get K Q by R square. So basically this is the formula for electric field intensity due to any capital charge Q, any charge capital Q. So it would be K Q by R square. You need to remember this formula. Okay, so let's go further. So this is the formula for electric field intensity, as I told you. Now the superposition principle also exists for electric field intensity. Like if you have more number of charges in a system and you want to calculate the electric field due to all of these charges, then you can see over here we have Q1, Q2, Q3 and Q4, and we are calculating the resultant electric field at this point due to this and this charge. So you can see that we have E2 over here due to charge Q2, E3 due to Q3, E1 due to Q1 and E4 due to Q4. Okay, so the resultant, the superposition principle says that the resultant electric field at any particular point due to a system of charges would be the vector sum of the individual electric field intensities. As you can see over here, E equals to E1 plus E2 plus E3 plus E4. Okay. Yeah, okay, so superposition principle, I hope it is clear. Like when we talked about the force, superposition principle for force, so the resultant force was vector sum of the individual forces, and for electric field intensity, it is like the vector sum of electric field intensities due to individual charges. Okay, so that's superposition principle in this case. Okay, so electric field, we were talking about electric field. So try to imagine how this electric field would be there. So this electric field, to understand that what would be the pattern of this electric field, you need to understand the concept of electric field lines as it is shown over here. Electric field lines are what? These are just imaginary lines which show the pattern of electric field due to any positive or negative charge. Okay, like you can see over here, it is a curve drawn in such a way that the tangent at each point on the curve gives the direction of electric field at that point. So this is like, I'll explain it to you. Like if you have an electric field like this at any point, so if you want to calculate the direction of electric field at this point, so you have to draw a tangent over here. So this would be the direction of electric field at that particular point. Like let's say this is point A. So at this point A, the direction of electric field would be in this direction, and this, the curve which we made, this is the electric field line basically. Okay. Okay, so let's go through the other properties. Yes, so the important properties of field lines would be that field lines are continuous curves without any breaks, and two field lines do not cross each other. Now, why do they do not cross each other? This is basically like if you have the electric field lines crossing each other at any point, like let's say one is this and the other is this. Okay, these are two different electric field lines. So at this particular point where they intersect, if we draw a tangent, then there would be one tangent would be here and the other tangent would be somewhat here. It's not touching, so you can understand like the graph would be, the curve would be something like this. So this line, this is also the direction of same electric field, and this is also direction of the same electric field. So basically we are getting two directions of the same electric field, which is actually not possible because we are drawing the electric field lines for the same electric field. So it is not possible to get two directions of the same electric field. Okay, therefore two field lines do not cross each other. Then we have electrostatic field lines start at positive charge and end at negative charge. This I'll explain it to you with a diagram in the next slide. And these do not form closed loops, you know that they emerge from positive charge, end at negative charge, but they do not form closed loops as magnetic field lines make. This you will study in the next chapter. So let's go through a diagram of this. See, this is a representation of the electric field lines due to a positive charge. Like see, in this the lines are going outwards, and in this the lines are going inwards. Why? Because negative charge is attractive in nature and positive charge is repulsive in nature. That like it will, like if you place a test charge over here, it will then push it in this direction, or it will exert a force in this direction, while this would attract it. It will attract a positive charge. Okay, that's the difference. So these are the imaginary field lines which show you the direction of the electric field. Okay, now let's see if they are placed together. If positive and negative charges are placed together, then this would be the behavior. Like if you have dissimilar charges, positive and negative placed together, then this would be the representation. They would start from positive and end at negative charge. Okay, and this is like just an example. Like if Q2 is greater than Q1, then you can see as Q2 is greater than Q1, like Q2 when we talk about, so this one is Q2 and this is Q1. So you can see as Q2 is greater than Q1, so the number of field lines is also greater than. So like if I say n is the number of field lines of Q2, so Q2's number of field lines is also greater than Q1's number of field lines. Okay, so this is a phenomena. The more number of field lines, it represents a powerful charge, or you can say a greater electric field over there. Okay, so the next concept is electric dipole. What is a dipole? Dipole means like when two similar charges are placed at a particular distance apart. Like if one is a positive charge and one is a negative charge, if they are placed over a short distance apart, then that is called a dipole. So you can see over here that we have two charges, plus q and minus q, placed at a distance of 2a apart. So this is a dipole. Okay. Next, dipole length. Dipole length is 2a. And the distance between these two charges is called dipole length. You have dipole axis. Dipole axis is like the distance between these two charges. You can see over here, this is the distance, and the axis means this dotted line. This shows you the axis. Okay. Then you have electric dipole moment. This is a very important thing. You should just remember it, that the electric dipole moment of a dipole would be q into 2a. Simple. It is a product of q charge and the distance, which is 2a. Okay. This is electric dipole moment. So the next concept is electric field. Again, electric field due to a dipole. Like a dipole would also exert some electric field. We have two charges, positive and negative together. So they would surely exert some force to any other charge placed nearby them. Okay. So here, let's have a recap. The electric field due to a point charge was F by Q. So similarly, we have derived this formula for electric field due to electric dipole at in its equatorial plane. Now, what is equatorial plane? Equatorial plane, when we talk about, so like as I told you, this was the dipole. Okay, this, like, let's say one charge is here, one charge is here, -1. So any plane perpendicular to this axis, this was the axis. So any plane perpendicular to this axis would be the equatorial plane. Okay, you just need to remember this. So the formula for this, as you can see over here, we have mentioned the formula over here. Just a moment. Okay, so we have the formula over here. Electric field due to an electric dipole in its equatorial plane, it is minus p by 4 pi epsilon naught r cube. So you can also mention it as kp by r cube, minus kp by r cube. Now this negative sign, this shows the direction to be opposite to the electric field. That's it. Okay. Then we have the electric dipole at axis. So for an axis, it would be twice of kp by r cube, and this would be positive. Okay, that is, the previous one was negative and this would be positive. That's only the difference. Okay, so there is one more thing, like if two charges, if this dipole, if this positive and negative charge, if it is placed in an electric field, let's say this dipole is placed in an electric field, then obviously that electric field would exert some force on the positive charge as well as on the negative charge. So that would create that dipole to, like, it will lift, the force would be in opposite direction for positive charge and negative charge. So it will lift the dipole, and this effect is called torque. As you can see over here, it is mentioned over here. See, here it is, torque. Torque equals to P cross E. Now P cross E, what do you mean by P cross E? It is like cross product of momentum and electric field. Okay, so this is called torque. Okay, so let's go to next concept. It is electric flux. Now what is electric flux? Like when we have an electric field, so there are a lot of electric field lines. So if we put a surface, like just imagine a surface in a perpendicular direction in an electric field. If we put a surface in an electric field in perpendicular direction such that all the electric field lines are crossing that surface perpendicularly, so the number of field lines which would be hitting or which would be entering into that surface perpendicularly, that's called electric flux. As you can see here, it is the total number of electric lines of force passing perpendicularly through a given surface area. Okay, so that's electric flux, and flux density is like the number of field lines passing per unit area. Okay, so it should be perpendicular. Just remember one thing, it should be perpendicular. Okay, okay, so the formula for calculating electric flux would be E dot A, that is the dot product of the electric field and the area itself. Okay, and the SI unit, you should remember the SI units of all the entities which we have discussed here. Okay, force, electric field, now electric flux. So SI unit of electric flux is Newton meter square per Coulomb. Okay, okay, so This is the formula. Like if you have a surface, if you do not have a uniform surface, if you have a extended object, then to calculate the surface, then to calculate the electric flux, you would have to use integration, as it is mentioned over here, integration of E dot ds. Now this ds would be the small element of that whole area, of that whole surface area, which we would be taking, and then we would integrate it to find out the flux over the surface. Okay, so for this you have a Gauss theorem. This is the most important thing of this chapter, which is Gauss theorem. So this says that the total normal electric flux over any closed surface is always equal to 1 by epsilon naught times the net charge enclosed by the surface. So what you can understand by this is, like if you have charge q, then the flux, this is how we mark flux, this is the symbol for flux. So you can write it as equals to q, if q is the total charge enclosed, upon epsilon naught. This would be the flux. Okay, total charge enclosed was q, and this was the symbol for flux. Okay, this is Gauss theorem, and here it is shown the flux linked with the entire closed surface would be integration of line integral. Now the circle on the integration shows that this is a line integral. We are talking about the enclosed charge. Okay, so this would be q net enclosed charge upon epsilon naught, as I told you. Okay, this is how you calculate flux. So you can use this Gauss theorem to find out electric field due to an infinitely long straight wire also. So the simple formula over here is shown over here. It is lambda by 2 pi epsilon naught r and n cap. What is this n cap? N cap is basically a unit vector, which is, you can say that it is a radial unit vector in the plane normal to the wire. Like if wire is in x plane, if wire is on x axis, then this n cap would be along y axis simply. Okay, so what is lambda over here? Lambda is basically, it is linear charge density. Like we have let's say if we have L length of wire, then lambda would be the charge per unit length. Like you can mention, you can write it over here. Like you can write, if you are noting it down, then lambda would be charge per unit length. Okay, and in the next part we have electric field due to an infinitely thin plane sheet of uniform surface. Like previously we had this wire, and we have this formula over here, E equals to lambda by 2 pi epsilon naught r n cap. So here for this plane sheet we have E equals to sigma by 2 epsilon naught. This is the new formula for a plane sheet. Here what is sigma? Sigma is surface charge density, like charge per unit area it is. Okay, we have a sheet. Like previously we had wire. Wire means wire, when we talk about wire, we'll take length, and when we'll talk about area, this sheet, plane sheet, then we talk about area, because now we have both length and breadth both in picture, so we need to talk about area. Therefore we'll take surface charge density as sigma, this is sigma, and this is sigma, this one, and this is lambda. Lambda is what? Linear charge density. You can mark it up. Okay, so these are the charge densities, like what is the charge per unit length and what is the charge per unit area. Okay, so these are the two important formulas which you should remember, which you might be using in the numericals, and that's all about this first chapter. And please revise all the concepts, and till then, take care.